Hi guys, my name is Johannes Englsberger. I work at the German Aerospace Center, better known as DLR. The focus of my research is on light locomotion and whole body controls. Today's talk is entitled Who Would Dare to Work Side by Side with a Potentially Exploding Robot? And I'll share some thoughts and insights about the state of the art in whole body controls and some possible future extensions. So let's get started with my story. In the context of industrial robots, we find that most robots, still nowadays, but surely in early days, they have been fixed-based and position-controlled, coming with high precision and high reliability. However, there's an issue. There are several issues regarding security. First of all, the robot can clamp or collide with a human, causing severe dangers. Also, it might potentially collide with itself or the environment and destruct itself or destruct the environment. Similarly, as these industrial robots that we see here, we also find several humanoid robots in the research, such as HRP4C that we see here, which is able to walk, for example, quite nicely and advancing research clearly. However, there's always the risk of self-collisions, collision with the environment, and also, for example, clamping humans. So therefore, I personally don't see position-controlled, also humanoid robots or free-floating robots as a too perfect option. If we think about locomotion through unstructured environments, like dynamic locomotion, and also about safe human-robot interaction, what could be the solution? It clearly is torque controls or impedance controls. Why that? Because it is compliant, it's safe, isn't it? In order to convince you about the beauty, safety, and awesomeness of today's state-of-the-art whole body controllers, I'll show you 3 different simulations that are all beautiful. So let's start out with inverse dynamics. The stage is yours. Here it is, looking beautiful, natural, and nice. And as I'll show you in a second, you have close to perfect trajectory tracking. It's all fine. It's beautiful. So next on stage, we have the so-called passivity-based whole body controls, originally introduced by my colleagues Christian Ott and Maximo Rohr. Later, my former colleague Bernd Henze worked on it, and nowadays my colleague and PhD candidate George Messechon. So let's see how this one behaves. Simulation, once again, perfect. I could show you perfect tracking, all fine. As we will see later, this one is way more robust as compared to inverse dynamics. But in simulation, again, everything perfect. The final candidate for which I'll be showing a whole body simulation is the so-called MPTC, the Modular Passive Tracking Controller. This is a very generic concept. It can work for both fixed-based and free-floating robots. I presented it last year at RSS 2020, and this paper can be downloaded from the official RSS webpage. So let's have a look at its performance. Once again, you see perfect performance, perfect tracking, all perfect. So as we see, we can achieve close to perfect results in simulation, nice, beautiful, perfect tracking, all fine. How about real-world settings? Can we achieve highly dynamic humanoid or other like-it robots that are even safely interacting with humans? Let's have a look here. So how about that one? Atlas for sure moves very dynamically and beautifully. However, I would never touch it when it's in operation. So I wouldn't call that robot safe. The next candidate I'll be showing here is Talos. So here we see Hilario from PAL Robotics, who's interacting with it, balancing nicely. And as you can see, he's working in very close proximity to the robot. So no issues to be expected regarding safety. Also, Talos can walk, as you can see. However, as far as I know, its walking is based on position control, so not so safe right now. How about DLR? So in my research group, we're working with Toro, who we see here. We have achieved purely torque-based walking, like long step walking. This is George Messechon's work, like our PhD student, George Messechon. Also, we did like walk outside on grass. Here we go. Toro can traverse a mattress, as you can see here. So this is really compliant. You see the foot is wobbling all over the place, and it can traverse. We can do. We can traverse like stones, gravel. This is George on the background. Here you see it's sinking in and it's just nicely traversing the terrain. In the end, it's even wearing my shoes and like still works. Actually, worked better in this setting. So as we can see, torque control is like reliable and safe. Here I'm showing Toro walking based on MPTC, so this modular passive tracking controller I've been talking about, which is my personal work. It's also having some angular momentum, like some angular momentum based push recovery. And as you can tell, this robot is like safe and very huggable, as you see. I like to hug it. Yeah. Finally, let me give you a sneak preview into our live demo, which will take place during Humanoids on Wednesday, 21st, during the Worldwide Virtual Lab Tour. This video here was taken yesterday, and we see Toro like automatically detecting some stair and walking over it, based on pure and nice torque-based whole body controls, so the passivity-based controller of George Messechon. So you'll be seeing that on next Wednesday. You might have realized that I didn't show any videos of Toro walking in experiment based on inverse dynamics. We did achieve walking based on inverse dynamics. However, first of all, the tuning effort was roughly 2 years as compared to a few weeks when comparing inverse dynamics to passivity-based controllers. And second of all, we didn't achieve any performance, even like nowhere close to what we achieved with passivity-based controllers. So this is a big advantage of passivity-based controllers with regard to real-world implementation. They're much higher robustness. The presented passivity-based whole body controllers, they are so compliant, nice, obviously safe, that us researchers, we dare to touch the robot while being in the controls mode, to work around it, directly interact with it. And we even dare to let visitors touch it. By now, you might believe me that torque-based whole body controls for humanoid or other free-floating robots is totally safe. But did I tell you the truth? Totally not. What might happen? Well, if you worked with such robots, it might have happened to you that you lifted the robot up while the controller was running. What happens? The robot does explode. Did you ever see it like stepping into a hole? The robot does explode. There's basically, in the state of the art, to the best of my knowledge, there's two different types of controllers. There are the ones that do work inverse dynamics in combination with some heuristics. These heuristics are typically based on like some additional impedance terms, which the controller, like the actual controller, doesn't actually know about, and there's no stability guarantees anyways for such settings. However, the remaining state of the art, which works with, let's say, pure whole body controls, like inverse dynamics and so on, they all have in common, they will explode if you lift them up, they will explode or get unstable if they like trip into a hole or so. Let's quickly verify what I just said. So here we see Toro in the inverse dynamics based controller. So after initially just letting it stand here, I'm applying a tiny little bit more than its gravitational force to the robot. So basically I lift it up and let's see what happens. So standing still and explosion. And as you can tell, also from the slow-mo, this is a highly dynamic explosion, obviously. And I wouldn't like to stand there. And this is all based on the wrongness of the assumption that this point, for example, does not accelerate. So since the controller makes the assumption this point does not accelerate, which is totally wrong, everything blows up. The root cause of this issue is that state-of-the-art whole body controllers are highly sensitive to the correctness of the assumptions about the contact constraints. If the contact constraints hold, so for example, if the foot is firmly placed on the ground and it does not accelerate, which is typically assumed, everything works fine. Like all the math in the controllers works perfectly fine. But as soon as this contact assumption, for example, the assumption about no acceleration while tripping into a hole, as soon as this assumption is wrong, the complete math and the complete controllers, they explode, and so does the robot. Some time ago, I started investigating this issue in detail, and I'll present my findings during humanoids, namely next week on Tuesday, July 20, during the interactive session 1, where I'll be showing a poster. And here's the paper, just a very quick preview. It's called Relative COM to Foot, so RCF control, which yields high contact robustness. In the paper, I compare 3 different controllers, namely basically something like inverse dynamics, a controller that is based on MPTC, but an absolute formulation, like as presented at the RSS last year, and another controller that is based on this relative COM to foot formulation. And the model that this examination is based on is called the simplest articulated free-floating, or SAF model. It is based on just 2 links, point masses, a trunk and a foot, which are only able to move vertically. They have 1 actuated degree of freedom in between them, and the foot may or may not exert like ground reaction forces to the ground, like depending if it's there or not. And the controller does not know about the ground being there or not. Here I'm showing a MATLAB simulation for this proposed SAF model, so the simplest articulated free-floating model. It is based on 2 links, as I said, like the trunk and the foot that we see here. This is the center of mass. We also see the like joint torque in between these 2 bodies, like in orange or red. And this is the force acted towards the ground in blue. Also blue is the ground. At some point the ground will break away and the robot falls down, and it's, after some time the ground reappears. Here we see inverse dynamics, first of all, for a scenario where the robot is meant to stand still. Meant to stand still, free fall, and then still meant to stand still. Let's see how it performs. So it stands nicely, then the ground breaks away, and inverse dynamics blows up. This is perfectly the same as what we observe in real experiments when lifting the robot. When it's activated, it just explodes. In this case linearly, typically just in configuration space. Next up is an absolute MPTC formulation as proposed in the RSS 2020. Again, like during nominal stance, it converges nicely. When the ground breaks away, the robot poster basically diverges and blows up either. Both previously shown controllers, they're formulated in an absolute way. So an absolute COM controller and or an absolute foot position. Now in the proposed work, like in this recently proposed work, I'm using a relative COM to foot controller based around the concept of MPTC again. And now we'll see a different behavior. So nominally nice tracking, a free fall. It is like the controller is stable or bounded, and after the ground appears again, we have a nice recovery. So as we just saw, both inverse dynamics and the absolute MPTC formulation, they already explode in the nominally stationary case, so when the robot is just meant to stand. Now I'll show a dynamic trajectory tracking task, again for the relative CM to foot RCF controller, again for this standing, falling, standing scenario. As you can see, we have some nice oscillatory tracking behavior, some stable or bounded free-falling behavior, and again some nice oscillatory tracking behavior. Here I show like some plots over time, so you see this nice oscillation, some like bounded free-falling, and again this desired oscillation. This is the like desired and actual trajectory, so we have some initial convergence, some bounded errors during the falling, and again perfect convergence during and tracking during stance. This is the relative task error, so you see that it does converge nicely, has some bounded error, and again converges nicely. And here are the joint torque in red and the contact force in blue. Now looking at these very simple simulations, my first intuition clearly was that the last presented controller, so this RCF, relative center of mass to foot controller, would have the by far highest chances of success when porting it to a full humanoid robot, which is pretty obvious, I thought, because this absolute COM center of mass controller just exploded. The absolute MPTC based controller was close to an explosion, I'd say, while the RCF controller was just perfectly fine and bounded. However, let's have a look what happens in the 3D simulation. Now here we see Toro in a OpenHRP simulation. Now for the case of two relative center of mass to foot controllers, so RCF controllers implemented, one for the left foot, between left foot and center of mass, one for the right foot, from the right foot to the center of mass. And I would have hoped that this would just work now. But let's have a look what happens. So when lifting the robot, very unfortunately, as you see, the robot very quickly becomes unstable, even though the RCF formulation was meant to be much more robust as compared to inverse dynamics, for example. But it behaves pretty much the same, unfortunately. Now looking at the absolute MPTC formulation from RSS 2020, this controller shows a very surprising behavior to me. As you will see, in real time, it's still looking somewhat chaotic. However, if we replay in slow motion, what we find is that the behavior is much less explosive. So almost almost stable for quite a long time before becoming unstable. So this is really surprising to me, as this very simple model, the SAF model, basically showed that that this model might become unstable, at least for certain settings. Now, if we compare the three controllers, namely this absolute center of mass controller, like in inverse dynamics, this absolute MPTC controller, and the relative MPTC controller I just presented, they have, like the two exploding ones have one thing in common. Namely, both of them make the assumption that the foot does not accelerate. The assumption that the foot does not accelerate. Whereas, really interestingly, this absolute MPTC formulation, instead of making an assumption about the foot acceleration, it has two controllers, one for the absolute foot task and one for the absolute center of mass task. And although it's imperfect, although it makes assumptions about the contact range, which are obviously wrong, by not introducing this assumption on the foot acceleration, it looks like it behaves much more robust already, although it's still very much imperfect, that's for sure. So assumptions about contact constraints are bad or dangerous. But is that right? Isn't it maybe just a matter of my two complicated controllers that we have been examining? Let's have a look at the following two simulations and we will find out. Here I implemented a simple joint impedance task using my whole body control framework. But as I said, it is a simple and safe joint impedance task. As you see, the robot behaves perfectly passive, perfectly stable and safe. If we take that very same, very safe joint impedance controller and tell it about the contact constraint, it will believe, as we tell it, it will believe that the foot is not accelerating. Therefore, it knows, or it believes, it can exert forces onto the ground, which makes it balance much more stably as compared to not having this, telling it about this constraint. However, once I lift the robot up again, this pure assumption about the foot not accelerating, again, even for this very simple controller, makes the system blow up. So this is the key takeaway of my talk. Making assumptions regarding the contact constraints seems to be dangerous with regard to the robot's safety and obviously with regard to the safety of humans surrounding it. Right now I don't have a solution to this problem. However, in my ongoing research I will try to tackle the problem, and I also propose to the community to have a look and see if we can together solve it. Now almost all of my talk has been dealing with this problem of contact constraints. I do believe that when comparing inverse dynamics versus passivity-based or impedance-based controllers, passivity-based controllers have a much higher potential with regard to their final utilization, like next to humans, both due to their higher level of safety and robustness. It is, however, also important to note that impedance-based controllers, as compared to inverse dynamics controllers, have some particularities, for example, with regard to damping design and allowable stiffness. With regard to damping design, just choosing any damping, for example, a diagonal damping design, it comes with both problems of over-damping and under-damping. And this is configuration dependent. So therefore, in a traditional, very simple damping design, you're very likely to damp some degrees of freedom much too high, which makes you sensitive to, for example, noise in the velocity signals, or much too low, which leads to like excessive overswinging, which is very much undesirable. On the other hand side, the stiffness design is also of particular interest. There may be the issue of too high stiffnesses, which is also a configuration dependent problem. where too high stiffnesses lead to high local eigenvalues and therefore cause vibrations in real-world systems. The problem of damping design is quite well known in the literature and can basically be solved using double diagonalization. Here, depending on the configuration and so the inertia at hand, the damping is now automatically designed in a non-diagonal matrix in such a way that it's always, for example, critically damped. In contrast, to the best of my knowledge, the stiffness issue that I was talking about, so potentially too high stiffness values, they're much less treated in the literature, and thus I will also focus on this in my future research. So as you saw, this talk was very much science and controls related. I do, however, believe that before applying such robots in manufacturing settings or for a service robot, for example, first of all, these robots need to be 100% safe. And safety in this case is clearly controls related. Once we have solved these problems, let's apply those robots in the real world and alongside humans. So especially if you were patient enough to watch this complete talk, I thank you very much for your attention. I hope you could learn a little bit and make use of these thoughts and ideas in your future research. I'm looking forward to the open discussions during the workshop, and see you soon.